Hello there, Sunni Fung here. I hope you're doing well. Welcome to this video. So today, this video, I want to look at doing some thermal comparison testing on this graphics card, which I got. I unboxed this in one of my earlier videos. It's the MSI GeForce RTX 2070 Aero ITX. And this card is special for, one, you can't buy it anymore since MSI stopped making them. You know, NVIDIA, they superseded a 2070 with 2070 Super. So the next closest thing you may be able to get of this card is the MSI GeForce RTX 2060 Super. And second of all, it's small. It's 174 millimeters in length, and it's a very special card. In fact, it's ITX only. So, what testing am I looking to to do? I'm just going to go straight into the testing I have done. So, in this case, we're looking at the thermal testing. So I've been stress testing this to look at the thermals, look at the temperatures, and compare how it runs stock as well as with liquid metal applied. You replace it with liquid metal instead of stock thermal paste. How much of an improvement do you get? That's what I wanted to look at. So the test setup is very similar to what we had before. The only difference is that the CPU is now different. As you may have seen in my CPU cooler testing video, I decided to make the swap from an i9-9700K to an i7-9700K instead, due to very high thermals on the i9-9900K with my CPU cooler, even with a delidded CPU, custom copper integrated heat spreader, as well as liquid metal between all interfaces. If and when I do get a custom CNC machine copper IHS, I will do a comparison between the CPU, the 9700K stock, delidded with the custom copper IHS, and I'll also do a full liquid metal comparison as well on that. Anyway, so the test system: CPU, Intel Core i7-9700K, that's stock. The RAM is Corsair Vengeance Pro RGB, 32 gigs, speeds of 3200 MHz with CL16 timings. Motherboard's an ASRock Z390 Phantom-ITX/AC. Got a Sabrent Rocket 1TB NVMe SSD for storage device, and then we've got the enhanced ENP7660 80 Plus Platinum Flex ATX power supply, and that is a 600 watt power supply, and it's absolutely tiny. So the test I used for comparison purposes is Furmark V1.21.2.0 and at 720p, 8 times MSAA, and I used a hardware monitor and MSI Afterburner for monitoring thermals, clock speeds, and fan speeds. So before I jump into the results, I want to just show you, what happened in terms of the liquid metal application, because it's not something that most people would go out of their way doing. Most people buy the cards, they'll have warranty, they will be like, okay, I bought this card as is, I'll leave it as is, because, you fiddle with your card and something goes wrong, you may not be covered. So, first things first, got a video here showing myself taking this apart. So, had liquid metal, isopropyl alcohol to clean off the old thermal paste, a PH1 screwdriver for taking out the 6 spring-loaded screws, and yeah, you can see here now, starting to disassemble it. The screws are coming out. All of them out, trying to take this heatsink off. You've got to be quite gentle sometimes. I mean, it's surprising how much force you need to actually get the thermal pads to basically stop sticking. And yeah, to give you a quick look at the PCB there. So with liquid metal applications, you need to clean the surfaces off quite thoroughly. And so here you can see there's a copper base plate on the heatsink with 3 heat pipes sticking out the bottom. It's okay to use liquid metal on copper. What I will say is that it will tarnish it, and I have found that with my CPU cooler test as well. So when you use liquid metal and then you try and clean it off in the future, it will stain it. However, that should not really impact your thermals. So in this video, you can see I'm cleaning this, GPU die quite thoroughly to try and get rid of as much of the thermal paste as possible, because, you know, those, when they initially apply it, there will be thermal paste in between the surface mounted devices, also known as SMDs. And what I'm doing here now is cleaning things a bit more and then applying nail polish on the SMDs. The reason I do that is in the case that for some reason liquid metal does seep out over the edges of the die, you know, between the die and the cooler, you know, the last thing you want is for liquid metal to be making contact with your SMDs. The reason being, yeah, liquid metal is not just thermally conductive, it's also electrically conductive for those who aren't aware already. So I covered them all up, and then I gave them a few minutes to, you know, I gave it, you know, you can see that it's all been applied across surface mounted devices, and then I come back later on after allowing it to dry for a couple of minutes, and then start applying liquid metal. I don't like using the little syringes that come with the thermal grizzly conductor noughts packs, because you lose a bit of the thermal, the liquid metal, and it's a pain in the backside to use as well. So you can see here, you apply a little small amount on, and then you have to very slowly spread the liquid metal across the top of the die. You can't really rush this process. It's a really frustrating thing to do when you first do it, because it relies heavily on surface tension. So in this part now, you can see me pushing the heatsink onto there. I'm trying to see if I can get an imprint of where the GPU die would sit relative to the copper base plate, but I ended up just covering a large area and thought, you know what, that'll be fine, because what happens is the surface tension between the liquid metal surfaces would then stop it from, well, actually it wouldn't stop it, it would then adhere to itself. You use liquid metal on its own, it is not going to work. So there's that, which then leads me back onto the results. So the results, what can I say? Let's start with, there's two different scenarios that I've done here. So the first scenario is 100% power limit, and the second scenario is 114% power limit, which is the maximum power limits that the card will allow. So starting, there's a lot of information on the screen, so please, you know, just take it in slowly. If you want to pause the video here, please do. So I tested it at the card with Furmark, 720p, 8x MSAA, at various fan speeds. I'm saying various fan speeds, I mean, really, the only two I really properly tested were the auto fan curve and the 100% fan curve. The only exception to this is the 47% fan speed I tested with the conductor not applied as well. So, as you can see, all the cards, they seem okay for their thermals, in the sense that, yeah, it's, you know, 23 degrees for the ambient temperatures. It's like, it's looking all good. Do bear in mind that this graphics card has got a minimum fan speed of 47%. On MSI Afterburner, when I would try to lower the fan speed below 47%, it would automatically set to 47%. Is this really necessary? I don't know. I think, you know, MSI could have gone a bit more, you know, relaxed on the fan curve. You know, especially for the lower RPM, lower RPM, the lower temps, because, you know, with an ambient temperature of 18 degrees Celsius, this card's only running 5 degrees above ambient with 47% fan speed. You have loads of bigger cards which run at, you know, 40, 50 degrees ambient, ambient, idle. And, you know, the fans still aren't spinning up. So, you know, they could have dropped it to 0. They could have had it, say, 20 odd percent, but 47, it's slightly audible. It's not the most annoying thing in the world, though. So, on to the actual testing. So, the bottom two results we got here are for the stock paste. And then the top 3 results are for after liquid metal has been applied. This is thermal grizzly conductor knot. So, comparing the stock paste to the conductor knot at auto fan, there is a 3-degree drop going from the stock thermal paste to thermal grizzly conductor knot. 69 degrees with a stock, and 66 degrees with liquid metal. There are two other things that need to be factored in as well, and these are also very minor. So first things first, if you look at what clock speeds were being achieved, this is basically once the thermal have sustained for a period of time, and they have plateaued and flatlined. This is when I reset hardware monitor for it to then be able to log what the minimums and the maximums were for the clock speeds that were being achieved by the GPU core or GPU die, whatever you want to say. So with the stock paste, you're looking at 1725 to 1770 megahertz, and with conductor nodes, you're looking at 1725 to 1785 megahertz, which is they're very similar. At the top end, you might get an extra 15 megahertz. It's not that big of a deal. The next thing you'll notice on the left-hand side here, you'll see that the fan speed has dropped by a massive 1%. Yes, you heard that right. A massive 1%, which in this case works out to be about a 50 RPM drop. Is it something I could notice in terms of the sound? Maybe, maybe not. It's not really... It's more one of those where you see the numbers and you're like, oh, it's actually spinning slower, rather than I can actually hear it's a lot quieter. Yeah, it wasn't that significant of a difference, I don't think. So, I mean, the main takeaway from this particular test was we had a 3-degree drop. Then we look at the stock pace at 100% fan speed, and the conductor nodes at 100% fan speed. Bearing in mind, 100% fan speed is 3000 RPM. It's still relatively quiet, considering it's 3000 RPM, but it's still, it's definitely audible. Would I want to run it at the fan at 100% RPM? No, of course not. Anyway, comparing these two results, with the stock pace at 100% fan speed, we were looking at 58 degrees Celsius, which, for an RTX 2070 is very good, I think. But it gets one-upped by the conductor nodes, one with 55 degrees. Wow. 3-degree drop. And once again, you look at the clock speeds. At stock, it's 1725 to 1785. With conductor node, bang, 1740 to 1800, which is basically a 15 megahertz increase across the board. Yeah. So just looking based on the 100% power limit testing, you're looking at a 3-degree drop overall, and maybe 15 megahertz here extra on top. I also decided to test 47% fan speed with the 100% power limit with conductor applied. Why? I want to see what kind of thermals and clocks we're going to get. So you see here 75 degrees Celsius, and the clock speed at 1695 to 1755. So you're losing, about 30 megahertz compared to auto, but the graphics card's a lot quieter. I say a lot quieter. It is a noticeable amount quieter, but you are compromising your thermals. 9-degree difference is quite a lot. And this is this 75 degrees, but you got to bear in mind that we are talking about an ambient temperature of 18 degrees Celsius. It's quite a big delta. So, moving on to the 114% power limit testing. To sum things up, you get 73%. This is a very similar pattern to what you have seen in 100% one. So 73 degrees with the stock paste, 70 degrees with the conductor node. Funnily enough, at auto, the clock speeds are basically very similar. 1785 to 1815, 1785 to 1815. And the fan RPMs, they drop about 1 or 2%. Again, about 50 RPM difference. Based on that, I don't know how the percentage work there, but it's what MSI Afterburner showed. And yeah, so 3-degree drop, maybe a little bit slower fan speed. The actual core clock stayed the same. You got stock thermal pace 100% fan speed, you're looking at 63 degrees. Conductor nodes 100% fan speed, you're looking at 60 degrees. Once again, a 3-degree drop. So stock pace at 100% fan speed, you're looking at 1800 to 1830 megahertz. And the core clock for the conductor node, you're looking at 1815 to 1845 megahertz, which once again is about a 15 megahertz increase with a 3-degree drop to go along with it. Then I also tested conductor note with 47% once again, just for a bit of a laugh. And, you know, you look at 1740 to 1785 megahertz clock speed, which is good, which is basically the same as having it at stock. But you got a problem with that. You got 83 degrees on the GPU. It's quite toasty. I mean, the intention for this is, you know, for it to go into a small case. And I'm not sure what to make of that in this, you know, in the sense that it's quite high there. So, what do I make of this? Well, what do I make of this card on the thermals first? MSI have made a very good card here. The cooler is being used to basically the best potential it can, you know, for the most part already. 3 degrees. An extra 15 megahertz. If you get a card like this, or maybe a RTX 2060 Super Aero ITX from MSI, because you want to build something similar, or you want a card that's very similar to this. 3 degrees, 15 megahertz, maybe slightly slower fan speed. I don't know if you value your warranty more or a couple of degrees less. In my case, I don't have warranty. Why? Because I bought my card from China, and I can't really claim warranty on something that I bought from China via a Taobao agent. So for me, you know, it makes sense. There's also the fact that it's going into a very, very small build. Yeah, one thing I'll say is don't run the fans just, you know, at 47% forever. Do leave it, you know, I'd say just leave it on auto. The difference from 110% power limit to 114% power limit, you're increasing the power limit by 14%, you're only gaining about 50 megahertz unless you start doing some fine tuning and stuff. Is there really a need for it? I don't think so. And also the fact that your thermals go up a reasonable amount. From what I found, it goes up a couple of degrees, and it's like, is it worth the extra couple of degrees? You know, it's like about 5 degrees. It's like an extra 5 degrees. Extra 5 degrees, you get more noise. Are you going to get, you know, how much more performance are you going to get at 50 megahertz? It's not going to be much. So the final, you know, the final conclusion to this is, if you get a card like this, well, you probably won't buy one of these new. You'll probably buy the RTX 2060 Super Aero ITX. Just use it as it is what I'll say. Unless you really need, if you got a build which is so constrained that you really need to drop those extra 3 degrees, fair enough, do it. I mean, even for example, RTX 2080 Ti cards with, say, the triple slot XC Ultra cooler from EVGA. I've taken one of those apart before and applied liquid metal to it. I only saw an 8 degree drop in thermals at 100% fan speed when compared side by side, and maybe a slight increase in clock speed. So it's one of those. Do you need the extra thermal headroom? Most people probably won't. But MSI made a very good cooler here, and they've made a very good card. That's what I will definitely say. So yeah, that's it for this one. If you enjoyed what you saw, then please leave a like on this video. Subscribe if you haven't already. My next video will be a video overview of a build in the SGPC K39 V2, which will feature the i7-9700K, all the parts that I've been using for testing purposes, and hope, you know, it'll be a step-by-step video. I might have to, you know, fast forward it to try and compress it into a reasonable length. Otherwise, you know, you'll be here for ages watching a video of me building a PC. But yeah, that's something to look forward to. And after that, I might have some videos to update on things I'm going to be doing with that as well. But until then, thank you all for watching. I'll catch you in the next one.